Sanu and I am student of BSc Chemistry on a second year. Today we will read about topic Chemistry of Elements of second and third transition series. So let's read about the topic. General characteristics. Element shows a strong similarity in their chemistry with this group but show large difference from the elements of the first transition series. This similarity is due to filling of 4f orbital in the elements that lie between these two rows of element, atomic and ionic radii. As we move down, there is an increase in the size, increases from the first to second, but from second to third transition series, increase is negligible. There are 14 elements called lanthanides between La and HF. In these elements, penultimate 4f cells of electrons is filled. There is a gradual decrease in the size of the 14 lanthanide elements from Ce to Lu. This is called lanthanide contraction. The lanthanide contraction cancel almost exactly the normal size increase or descending. A group of transition elements, the covalent radii of HF and ionic radii of HF4 plus are actually smaller than the corresponding volume of Zr. On descending, one of the main groups of elements, the size of atom increase because extra shells of electrons present the elements of the first group in the D block shows the expected increase in size Sc by La. However, in the subsequent groups, there is an increase in the radius 1 to 2 pm between the first and second number, but hardly any increase between the second and third elements. This trend is shown in both of the covalent and ionic radii. Ionization energy, due to almost same size of second and third row transition series, they show almost same value of ionization energy. A particular feature of the third IE against atomic number is D continuity between Tc and Ru in the second row and Re and Os in the third row. This reflects the additional energies required to break into half-filled subshells. Oxidation states. The element of second and third row do not show identical pyramid of oxidation states as the first row. In iron family, Os and Ru show oxidation state up to 8. For example, OSO4 and RuO4, the highest oxidation states available to an element, is usually found among its compound with two most electronegative elements, fluorine and oxygen. So that an examination of the binary fluorides and oxidation of transition elements should reveal their maximum chemically attained oxidation states. Stoichiometric oxides and fluorides of the second and third row of elements are given in table. Binary compounds with less electronegative elements, chloride, might be accepted to show a slightly different range of oxidation state. The elements of second and third rows show maximum oxidation states. Of example, MO4 M equals to OS or Ru with oxygens and Re in 7 plus 7 in ReF7 with fluorine. The most common oxidation numbers of the transition metals are: for Y is plus 3, Zr is plus 4, Nb is plus 3 and plus 5. For MO is plus 3 plus 4 plus 5 plus 6, Tc is plus 4 plus 6 plus 7, Ru is plus 2, 3, 4, 5, 6, 7, 8. RH is plus 3, 4, 6. PD is plus 2 plus 3 plus 4 plus 6. Ag is plus 1 plus 2 plus 3. CD is plus 2. Reactivity. The element of first transition are more reactive than the elements of second and third. The lanthanide contraction is mainly responsible for the low reactivity of the second and third transition series. Example, gold and platinum are least reactive. Stability of the complexes. Transition metals have ability to form complexes. This is due to small size, highly charged ions and availability of vacant d orbital. The element of first transition series forms stable complexes with hard donors with nitrogen, oxygen, fluorine, whereas elements of second and third transition series from stable complexes, peace and heavier chalcogen donors. Magnetic properties. Magnetic moments are closely to spin-only value in the first transition series, but elements of second and third transition metal ions often observe a complex behavior. Compounds of first transition series shows high spin nature. The compounds of second and third are low spin nature. There are two main reasons for this. 4d and 5d orbitals are spatially larger than the third orbitals, so the presence of the two electrons in an orbital produce less electronic impulsion. A given set of ligands produce large splitting of orbital in case 5d and 4d and then of 3d. Metal-metal bonding. Metal-metal bonding is very rare in the transition series except in the metal carbonyls such as Mn2 CO-10, Fe2 CO-9. Carboxylic ions such as Cr2 CH3 COO4 H2O2. On the other hand, metal-metal bonding is very common among the heavier metals. For example, therefore, carbonyl with MM bond similarity to those of first transition series with Ru3 CO-12. Metals such as MO, Ru and RH form binuclear carboxylate complexes such as. However, MM bonding is more common in second and third row of transition element. A number of carbonyls are known of these elements with MM bonding. specifically carbonyl, which is not formed by first row transition elements. Lying chromium, MORU and RH formed by nuclear carboxylic complexes such as MO2CH3, COO, Vol4, H2O2, Vol2. Halides ions are known which have MM bonds such as Re2Cl8, Vol2 and MO2Cl9. The lower halides of several elements have a group of 3,6 metal atoms bonded together and cluster compounds. The compound NB6Cl12 2 plus and Ta6C12 2 have unusual structure. Both contain 6 metal atoms arranged in a cluster as the corner of an octahedral with the 12 bridging halogen atoms across the corners. There is an extensive MM bonding within the octahedron. Other examples are MO6Cl12, W6Br12, Re3Cl9, etc. Coordination numbers. The coordination number 6 is commonly found given octahedral structure complexes where the coordination number is higher than 6 is less common in a first transition series but common among second and third transition series. There are few compounds in which coordination number is 7. Geometry by coordination number 7. The coordination pairs defined by the donor atom is idealized 7 coordinate structures: monocapped octahedron, monocapped trigonal prism, pentagonal bipyramidal. Extraction is difficult due to the sizes of ZR and HF are nearly the same due to lanthanide contraction. They possess similar electronic configuration but now they are separated effectively by ion exchange and solvent extraction. Property and uses. Like titanium, both ZR and HF are metal, hard and corrosion resistant, and their melting point 1855 degrees Celsius and 2222 degrees Celsius respectively. They are resistant to acidic and they are best dissolved in HF, where the formation of anionic fluorocomplexes is important in stabilization of the solution. ZR reacts with the air at high temperature to give mixture of nitride, oxide, antioxide, nitride, ZR2O and 2. ZR reacts with air at high temperature to give a mixture of nitride, oxygen to antioxides, nitride, ZR2O and 2. ZR is used for cladding. ZR is also used to make alloys with steel, and ZrNb allows you to important superconductor. Their very high absorption of thermal neutrons by HF is turned to good use. HF is used to make controls rods for regulating the free neurons levels. The nuclear reactor used in submarine. Compounds of HR and ZR. ZR and HF shows oxidation states +2, +3, +4 and +5 is the stable oxidation state for both the metals. So most of the compounds found in +4 oxidation states. Oxide. On addition of hydroxide to zirconium solution, a gelatinous precipitation of ZrO2 and NH2O is formed, where is a variable ZrO2 of HF2 are stable halides. All the halides of the types MX4, where M equals to Z DAR or HF and X equals to FCl, BRI are known. Aqueous chemistry and complexes. ZrO2 is more basic as compared to TiO2. Therefore, it is virtually insoluble in excess base. The aqueous chemistry of Zr+4 is well known since it is doubtful for hydrolysis of Zr+ taking place. The hydrolysis ions is often known as zirconyl ions and written as ZrO2+. Noble character. The metal in the group have the highest electrical and thermal conductivity is known. They are the most malleable and ductile. The high enthalpy of sublimation and high ionization energy are reason why Ag and Au tend to be unreactive. Show noble character. The metal have positive E0 values and are thus below hydrogen in the electrochemical series. So that's all for today. Thanks for watching.